voltato improvvisamente alla gente che era lì e ha detto: la gente che cosa dice che io sia? Chi dice che io sia? E voi chi dite che io sia?
Vi prego, vi imploro, con umiltà e con fiducia, permettete a Cristo di parlare all'uomo.
Don Gius aveva capito il problema che avevo. Se la tua vocazione è vero, il tuo lavoro verrà fuori anche dai sassi.
Sorry, this is the last part where we are supposed to ask each other. Oh, yeah. That's what I thought. Oh no.
Di comunicare la fede agli altri, ma veramente insieme a loro riscoprire che cos'è la fede, che cos'è la fede per me. Portare Cristo agli altri, comunicarlo agli altri, è l'unico modo che abbiamo per conoscerlo veramente.
And I'll say, I don't agree at all with Stefano. See you later, thank you. Thank you, you'll need it.
L'iter communionis aiuta a comunicare all'esterno la ricchezza di vita, di giudizi, di tentativi, di opere che nascono dalle persone e dalle comunità. L'iter communionis è proprio la vita del movimento. Scrivete all'iter communionis le vostre esperienze, ci fate bene.
My maximum was in Armenia when we had 7,000.
Improvvisamente la gente che era lì ha detto: la gente che cosa dice che io sia? Chi dice che io sia? E voi chi dite che io sia?
Vi prego, vi imploro, con umiltà e con fiducia, permettete a Cristo di parlare all'uomo.
Don Gius aveva capito il problema che avevo. Se la tua vocazione è vero, il tuo lavoro verrà fuori anche dai sassi.
Di comunicare la fede agli altri, ma veramente insieme a loro riscoprire che cos'è la fede, che cos'è la fede per me. Portare Cristo agli altri, comunicarlo agli altri, è l'unico modo che abbiamo per conoscerlo veramente.
L'iter communionis aiuta a comunicare all'esterno la ricchezza di vita, di giudizi, di tentativi, di opere che nascono dalle persone e dalle comunità. Litere Communionis è proprio la vita del movimento. Scrivete a Litere Communionis le vostre esperienze, ci fate bene.
Civiltà dell'amore. Fratelli e sorelle, costruite senza stancarvi mai questa civiltà. Lavorate per questo, pregate per questo, soffrite per questo.
Good evening, ladies and gentlemen.
Benvenuti.
Welcome to this session. Just like every year, at the meeting, we have this opportunity to take a closer look at a topic at the frontier of science, which concerns an area of nature that, thanks to research, we are able to approach. And given the title of this year's meeting, inviting us to reflect upon what is essential, we thought that we could focus on something that is really essential for each and every one of us and for any other form of life that is known. It is the fact that we live on a planet. And we live on a very particular planet, an extraordinary planet, our Earth. And there is an exhibition about it in the scientific area of the meeting here at the trade show. You're all invited to go and visit it to appreciate all the extraordinary features of our planet. But the Earth is not just the only planet. There are the 8 planets of our solar system, and there is an infinite multitude of planets around other stars. But the very fact that planets exist, that is, that nature invented such a planetary environment, is an extraordinary fact, and it is not to be given for granted. The creation of these planets is something complex. And today, astrophysics is able to start understanding how planets are formed. So this is today's subject. And as always, when we have these sessions, we have 2 big protagonists in this type of research. So let me introduce them right away, starting with Mr. Stefano Facchini.
Grazie. Thank you.
Stefano is professor of astrophysics at the State University of Milan. He earned his PhD at the Institute of Astronomy in Cambridge, and then he had research positions at the Max Planck Institute for Extraterrestrial Physics. And his supervisor was Ewine, and We'll introduce her in a minute. And at the ESO in Garkin. His research focuses on the features of the chemical and physical conditions of the planet's formation and on the discovery of planets in the clouds, in the soft clouds, thanks to which these structures are formed. Recently, he obtained an ERC grant, a very important type of grant, and he's also in charge of a program that is called ESO-ALMA, which is a great scope program to look for hidden planets in protoplanetary disks, something we will listen to this evening. And he also guides many programs for the direct imaging of JWST for these planets. And last February, Stefano was the protagonist of an important discovery published in Nature Astronomy, and it had a really important impact in the release of ESO on the particular role that water plays in the formation of planets. Thank you, Stefano, for being here with us.
Ewine
van Dishoeck. Ewine is one of the top world experts in the field of planet formation, astrochemistry, and of the physics of the interstellar method. She's professor of molecular physics in Leiden University in the Netherlands, and she had research positions in Harvard, Princeton, and Caltech. And the impact of her work is really extraordinary. It is enormous, above all for the innovative way in which her work joined chemistry with physics to understand these astrophysical processes that are really complex. And she had an important role in the design of new generation telescope like the JWST ALMA, and she earned an incredible number of awards. I will just quote one of them, which is the Kavlik Award, the Kavlik Prize, which is equal to the Nobel Prize. Ewine is also part of many national academies, as in the Netherlands, the United States, in Germany, in Norway. She is member of the Pontifical Academy of Sciences, and she was also president of the International Astronomy Union. And I would also like to say that Ewine has grown up a generation of astrophysics. One is Stefano, but he's not the only one present here today. At our lunch, there were 3 or 4 more people. They are her sons, scientifically speaking. And this attention to education, to training of science in the scientific field of young people is really equally important to her scientific contribution. And last but not least, she is passionate with art, inspired by astronomy. So thank you, Ewine, for being here with us.
Thank you.
Bene, allora.
Right, we're ready to start. And I would like to begin with Stefano, so that he can tell us about something about his research of this extraordinary and complex process and vital process which concerns the formation of planets. You have the floor. Thank you, Marco. We decided to give this presentation standing because that's how we are accustomed to when we present our scientific results. But before starting, I would like to say thank you again to Ewine for being here, because this work with her when I was at the Max Planck Institute in Germany was an essential part of my growth and professional profile. Thank you again, Ewine, for being here. And going back to what Marco said in the introduction, I will try to give a few hints, scientific hints, at some points that may answer immense questions. What are the physical mechanisms and partly chemical mechanisms whereby the university, in its all great complexity and enormity and order, is able to lead to the development and construction of systems that are so small and accurate and precise that are planetary systems. We live in one of them and we take them for granted. But scientifically, we will see that it is the result of a very complex process. And the physical laws and the initial conditions of universe cannot be taken for granted to be leading in a uniform way such a flower, final flower, that are planetary systems. And what is that determines their properties? I will show you some slides during the presentation to help understand you what I'm saying. For hundreds of years, human beings have always been accustomed to considering one solar system that is our. It concludes 8 planets, and for a long time we have known that there are 2 types of planets: the internal planets, the rocky planets like Mars or the Earth itself, and then external planets, exoplanets, that can be classified as gas giants, like Jupiter. Please consider that all the pictures, the figures that I show you are scientific figures with data. The only simulations that I'm going to show you, I will specify that, so you will know whether these are images or simulations. And considering this solar system, we have a question that we all ask. That is, what happens in the sky above us, in this such a big structure that is our galaxy? And now we just zoom in. There are 200 billion stars in our galaxy on top of us. Around each of these dots, whether we see them or not in the night, at night, they are above our head, they are around us. Well, around these stars there are planets. And what kinds of planets? How did they form? Since 1995, more or less, science has highlighted that the number of planetary systems is immense. This is the only scientific chart that I'm going to show you. What I'm showing you is a chart where in yellow there are the dots of the solar system. Every dot is a planet. The more we go up, the larger are the planets, like Jupiter. And the more we go to the right, the more far we go from the star around which they revolve. And the gray dots are planets that revolve around stars that are not the Sun. And we observed more than 2,500 so far. And we got a few conclusions from this. First of all, that on average, in the proximity of our solar system, every star has at least 1 planet. That means that the mechanism of planetary formation is extremely efficient. The second point is that these planets show a great variety, a great diversity in their physical properties. We can see that because the gray dots do not match the yellow dot. It's not that because there's something missing there, but that's because there is great diversity. And this must depend on how planets themselves are formed. Let's zoom into a region where now planets are being formed. Let's take a look at this video where we have the Milky Way on top of us, and we go to the Taurus constellation. You can recognize that, the orange part, and we have a molecular cloud here that Ewine will talk about in more detail, and we keep zooming in. We see visible light, but we will shift to infrared, which is a different kind of light, to have a better insight. And in a moment, we will start radio waves. So we will look at this very same system through radio waves. That means that we will see very cold material, and that's what we observe. At the center, there is a star that we cannot see with this type of light, and around we see this ring structure. This ring structure lays on a plane, and we call it protoplanetary disk. It is one of the systems where we think now planets are being born. In a minute, I'll go back to what we are seeing in this image. We see small dust grains that deliver some light that we can capture with our telescopes, minus 250 degrees. This is the same system, just turned on the other side, and you see the typical length of these systems at the bottom left. The diameter is about 400 the distance between the Sun and the Earth. This is another image of another protoplanetary disk with the ring structure. They are a little bit larger than our solar system in this case. And what are they formed of? In 1%, they include dust or small pebbles, about 1 millimeter, 1 centimeter, and the great majority, that is the 99% of these, are formed by gas, as you can see in this picture, especially molecular hydrogen, helium, but also CO, carbon monoxide, that we can observe from the Earth. How are these planets formed? In a very simple way. The big molecular clouds that are tens of thousands of AU, astronomical units in size, little by little they start collapsing on each other because they feel the gravity on all their sides, and collapsing on themselves. They have a tiny rotation, and as they collapse, they rotate in a stronger and stronger way for very simple physics reasons. And what happens with these rotations is that a flat disk is formed. It is in this disk that planets are formed. This is a protoplanetary disk, and that's why our planets in our region are on the same plane, because they were born in this structure. And the image that we have just seen was a reconstruction, was not a real image. What happens in this disk, and how are planets formed in this disk? There are two main ways. The first way is called gravitational instability. It is a little bit complex. We have a simulation here. When the disk has a lot of mass, by rotating around the star, what may happen is that small parts of the disk become unstable, and some gas may collapse on itself, creating big grains of gas, big clots of gas, about 10 times the mass of Jupiter. That's one of the ways we believe the biggest planets, the more massive planets, may be formed around the stars. That's not just in theory, because recently we started capturing this type of image, which is the image of a gas, of a disk, a protoplanetary disk, which from the spiral structure is clearly going into a process of this kind of gravitational instability. But the interesting thing is that this process forms just a few of the planets we have seen so far. So it's not the dominant one. Which is the dominant one? The one we think is more dominant is called core accretion, that is the growth of a nucleus. So it doesn't matter if you don't read the words in this chart. It means that the dust of 1/1,000,000th of a meter inside this disk, little by little, can stick a little bit, can clot and grow and become as big as, for example, the Earth. So that means that from particles that are as big as 1/1,000,000th of a meter, we have to get to something that is as big as 10,000 kilometers of array. So it is 13 orders of growth. That these 13 zeros, one next to each other in terms of dimension growth. That means that we have about 50 zeros as a growth in the mass of these systems. So we don't have the time to get into the details of the mechanics of this system, but what I can tell you is that many questions around how these small dust grains may grow little by little to get to form planets like Jupiter or the Earth are still open. So these are still open questions, and the research field is very open. But what the universe tells us is that this process is the result of many complex processes, and it is incredibly efficient. It works incredibly well, so well that we are here today and we are talking about it. So what can we do to look at and find these planets and make observations to find out whether these mechanisms work? We use some types of telescope, and we'll show you data from two particular telescopes. One is ALMA, the one I prefer because of its history, and that's the one I use the most when I manage to get data. It is a group of antennas that are at 5,500 meters in Chile. The other one in the Anatara plain, and the other one is a set of telescopes with infrared system that are called Very Large Telescope, and again under the ESO, that is guided by Europe and Italy too. Observing these stars that are born and are at the center of these disks, we have understood that if not all the systems where the planets are born today, but most of them have these substructures, these rings and these empty spaces, just like the rings of Saturn. Here we still see the thermal dimension of the dust, and we can still see the image of how these disks are visible when we see the reflected light from the central star. This is the image, so to say, of a reflected light in infrared. You see that the disks are not clean, but they have understructure. They have rings, they have spirals. And why is it so? What does that mean? We believe that these systems are structured that way because they are interacting with planets that are being formed there, and we went to look for them. This seems to be an image that is not particularly interesting, but if you focus on these 2 points, at the center there is a star that is covered by a small disk, not to burn the camera behind the telescope, and this light point shows you the first planet that is being formed in a system outside ours. If we take a step backward mentally, I believe that you can realize how impressive this can be. Our system is more than 4 billion years old, and now we are able to witness to the birth of a new world. And using radio waves, we could observe the same system, but realize that the dot is on another side. It is on the right. It is not below. And what did we understand? We understood that this system where planets are being born is hosting 2 planets that are being formed. These are called the BDS 70b and 70c They have these strange names, and this dot that we see on the right is nothing but dust that we believe is forming moons around a planet that is being formed. So we don't just see planets being formed, but also moons being formed. How can we observe these planets in other systems? Because it's extremely difficult to find them as they are being born, as they are being formed. By the way, I forgot to say, how long do they take to be formed? About 10 million years. That in astrophysical terms, that's a very short time. Everything is very relative indeed. We will now see a simulation here that tells us that when a planet is immersed in a protoplanetary disk and revolves around it in the gas, there are spiral-shaped forms because there are waves. It's like ripples created in a pond when we throw a stone there. The same happens here when the planet is formed, that it works like a stone that alters the orbital system, the orbital structure of the system. As we can see spiral in the gas, in the dust we expect to see rings, which is exactly what we saw before. And this tells us that probably, if not all the rings that we saw, but some of them, tells us that here there are planets being hosted that have just been created. And how can we see if these spirals are there? This is part of the research I have worked on over the last few years. And consider the analogy I've just mentioned. We have a little duck here in a pond, and the duck creates ripples and waves that are cone-shaped. If we take this cone and we put it in a rotating disk, it will form all those spirals that we saw before. It is a concept in physics, quite easy one. So what did we do? We went to look for these minor perturbations in these disks. This is a work that we have done in the last 3 years. It hasn't been published yet, so it's a preview at the meeting that we're giving you. These are some of the images of these protoplanetary disks in the gas. Colors change because they are radio waves, so we have to map them with visible colors. But what we can do and what we have managed to do is that we could see in a very accurate way the speed of these systems. And if we take the speed of rotation that we know very well and we take that out, it is the speed of these waves that propagate in the disk. To the left we have the data, in the middle there is the model rotating in a normal way, and to the right we see the results of these waves, small waves that emerge in our accurate analysis of data. And what we see is that these disks host those spirals that had been forecast owing to the interaction of the planet and the dust. Not all of them, but some of them. With this data, we are able to see gas that moves at 10,000 billion kilometers from us at a speed of 10 meters per second. That means that I could be able to see a person running in this on this stage. We do this at 10,000 billion kilometers away from us. And that's the level of the technology we managed to develop to get this kind of information. We have other spirals here, and the last point I wanted to mention is that there is a particular area where these planets may be created. It is the transition area where this disk is so hot, where we have water steam, and it turns very cold, and so water is ice. We call this transition zone snow line. I think it is clear what it means. So the water from steam condenses and it sticks to these grains and they grow easily, and so they can get to create planets. We think that Jupiter was created in this way. What were we able to do? We went to the same system I showed you before, HL Tauri, and what we managed to do for the first time was to be able to map the water vapor at the center of this system. And what is this telling us? So I can conclude here to then give way to Ewine's presentation. I can conclude by saying that we have images that tell us that the properties of the matter in such a very small size in quantum terms, they decide that they basically influence and decide over mechanisms of formation of planets, and all these mechanisms may have had a role on the creation of our solar system as we know it. So there is an intrinsic link between the properties of physics in the infinitely small in its shaping with the physics of the extremely big, that is the universe in its entirety. And for what we're talking about tonight, it is planetary formation. So it is now time to leave the floor to Ewine, who is the best expert on this subject. Thank you.
Prego.
Buonasera. Good evening. My apologies for not being able to speak to you in English. I speak in English, speak in Italian, but it's really a pleasure to see all of you here, so many of you. Fantastic to be here. So I'm going to continue, actually. I'm going to continue on the story that Stefano started. And I'm going to do that in a number of slides. But first, I really want to thank all of the young people that I have had the privilege to work with, and Stefano, but also several others that are here in the audience. It's really thanks to you that we have all these beautiful results. Good. So, Stefano talked already about the night sky. And here in the Dolomites, you have a beautiful night sky. And you can still see not just the planets, but you can also see the Milky Way. And immediately you then start to think, you know, where do we come from? And what is our place here in this universe? And you can go to Immanuel Kant, who said basically that the most important things are, you know, the starry sky above me and the moral law actually within me. So our origins actually start in these dark clouds, in this Milky Way. And one of my hobbies is astronomy and art. And as a Dutch person, I don't have to go very far. You see here Vincent van Gogh, The Starry Night. But also, other side of the world, Australia, the indigenous people, have this beautiful Milky Way dreaming, integral part of their way of life. And here, please go and see this beautiful exhibition by William Congdon here in Rimini. Several paintings of the moon are actually there. So we've talked already about the diversity of exoplanets. And we know that every star has at least one planet. There are more planets in our Milky Way than there are stars. But we have Earth, we have Jupiters, but we also have a kind of planet, super Earth, and mini Neptunes that we do not have actually in our own solar system. And that now raises the question, what is their composition? Could they be habitable? And that is what we're going to talk about. And directly linked to that is also the question, how were we formed some 4.6 billion years ago? We get information on that from asteroids, but we also get information from comets. Comets are not just rock, but they are rock plus ice. And we've had some very exciting mission actually to these systems. Now I'm going to spend quite some time actually talking about the newest facility that we have in order to study these questions. And that is the James Webb Space Telescope. And this has really been a 30-year journey in order to get to this moment. And there you see in the corner you see the last stage. Webb is going away. You see actually the solar panels coming out. Very emotional moment. Bye-bye, Webb. That was the last that we saw of it. So it's really thanks to thousands of engineers and technicians and managers that we have this fantastic mission led by NASA, but also with very strong European involvement, actually. My own involvement with Webb started more than 25 years ago through committees and being part of building one of the instruments actually on Webb, the so-called mid-infrared instrument. Where is Webb now? Well, Webb is actually, when you look here at the Earth and then the Moon, and you go 4 times further, 1.5 million kilometers, then you get to where Webb is at this moment. And it's traveling with the Earth around the Sun, in a place where we always have the Sun and the Earth and the Moon on the same side. Those are the noise. Those are interfering with our signals. A big sun shield actually protects us from that. So what makes Webb actually unique? Well, it's big, 6.5 meters. There you see a one-on-one scale model. And you see that it is really huge compared with a whole set of human people next to it. But Webb is special also in other ways. Its eyes do not look at what we see with our own eyes, the colors of the rainbow. You've heard Stefano talk about radio. You all know about the X-rays. Where is Webb? Webb is actually in the infrared part of the spectrum. So, because that is obscured by our Earth's atmosphere, we actually have to go into space. Now, Webb has several instruments actually on board, 4 instruments. You have cameras with which you can make nice pictures, but you also have spectrographs that actually unravel the radiation in the colors of the rainbow. And that is what we actually use in order to study our chemistry. And these are very sophisticated spectrographs actually that we make. And why do we choose to go to the infrared? That's partly because we then actually able to peer into the dust clouds that we see here, where the stars and planets are being born. So let me actually take you on a journey and follow the building of Webb. How did such a big facility actually come together? Here's our instrument that we built already between 2002 and 2008. Long time ago. It was shipped to the UK, then it was actually integrated and delivered to the US in the NASA Goddard Space Flight Center near Washington. And there all the instruments were put together. There the telescope was built. Remember that golden eye that you see over there? The instruments were put on the back of that telescope. And then from Goddard, it was flown to Houston. Now, several of you here in the audience will remember the importance of Houston. Houston, we have a problem. That's from the Apollo missions. That same test chamber is still available. And that was actually used in order to test the Webb telescope with all of its instruments. So that happened actually in Houston. Then from Houston, it went to Los Angeles. And that is where the sun shield was actually attached to it and was also fully tested. That was essential in order to cool the telescopes. Then from Los Angeles, it went to French Guiana. That's where the launch site is of ESA. It went there by boat. Fortunately not hijacked somewhere along the way. And then it went to the launch site, and that is where it was integrated into the Saturn V, not the Saturn V, the Ariane 5 rocket that you see actually over here. Now, why that particular rocket? It's the one with the biggest nose. So Webb had to basically fit into the nose of the rocket, only 4 meters. It had to be basically wrapped around like a little origami packet and put in the nose there of the rocket. And then it was actually launched. And then it had to be actually unfolded into space. And so many things could have gone wrong, but they didn't go wrong. They actually all went all right. And then we were very, very relieved when a few months later we got these first images. And we saw that our cameras and everything was working well, that we got these very beautiful, sharp images. Big, big, big relief. And now, on a daily basis, we're getting these beautiful images here from Webb. Here you see an entire galaxy. The red part, that is our MIRI instrument. The blue part, that's the stars, actually, that we have, the shorter wavelengths. So what we see is actually that this particular galaxy is full of forming stars. Here's another example, burst of star formation going on. And many, many more, just one beautiful image after another. And you can go to the website, webtelescope.org, and you can actually download them all yourself. So let's now actually go back to our clouds. So you all recognize this particular constellation, I think. It's Orion. But what is actually in between those stars? The region between those stars is not empty, but it's actually filled with a very, very dilute gas. And the thicker concentrations of that gas we call clouds, like the Orion Nebula. Now, these clouds consist of gas and also these tiny little dust particles. But the gas, it's not quite the periodic table that you know from high school. Hydrogen is by far the most abundant, followed by helium, but that doesn't do much chemically. The chemically more interesting elements, carbon, nitrogen, oxygen, the elements of which we are made, they are present in only tiny amounts. A fraction of a promille actually is happening. And so the big surprise came actually that there was this very rich chemistry going on in these clouds in spite of the big emptiness. And these clouds are indeed very empty. If you look here at some of these images of these dark clouds, then they have on average only 10,000 particles per cubic centimeter. That's 1,000,000 times less than what we have here on Earth in a very high vacuum. So what an astronomer calls dense is much, much more empty than anything we have here on Earth. And it's also very cold. And then we have these tiny little dust particles that Stefano was already talking about that actually absorb and scatter the light and make these clouds look dark. Just like when you have smoke in the atmosphere, then also you cannot look actually very far. Now here we were looking at the Carina Nebula with the eyes of the Hubble telescope, the light that we can see with our own eyes. Now we go to Webb, and we get these beautiful images here of these clouds. This is the same cloud, but now seen by actually by Webb. And what you see here, actually the orange part is the cloud, and all the little red dots in it are new stars that are being born. Some of them are pushing away the surroundings with outflows. Yes, here also another one, pushing away there with a bow shock that you see here in this cloud. Also the famous pillars of creation, now actually seen with the eyes of Mary. And you see actually these little dots, those are young stars being born at this very moment there in these clouds. This is another new image from Webb of a protostar that is still very deeply embedded in its cloud. But you see already these jets with which it tries to basically push away the surrounding material. Well, Nature liked this paper a lot, and it put it on the cover, and it said, "A star is born." Literally, a star is being born here in this particular cloud. So, how do we observe the molecules here? Stefano talked about ALMA. That's when we can see the molecule actually rotating. But the molecule can also vibrate. You know, we can stretch and we can actually bend. And that is the signatures that we are observing actually with Webb. And that allows us to actually see different kinds of molecules than we can observe with ALMA. And not just in the gas, but even also in ices. So here we have water, but we have a whole set of more complex molecules that we have now detected through their signatures, either with ALMA or with Webb. In all of this, water plays a very important role. So what form is water actually? It is present as a gas. It is present as an ice. But it's not present as a liquid, except on the surface of a planet. So with Webb, we can actually now see some of these ices. This is actually from some of our own work that has recently been published, where we're actually looking for the signatures of these vibrating ices actually in the signature of a background star. And this is a bit of a technical figure, but what you see here, these big dips, those are the signatures of water ice, of CO2 ice, and of carbon monoxide ice. This is what we can now measure really with Webb. So thanks to this work and also previous work and simulations and laboratory experiments, we now think that we know how water is actually formed in space. We think that it happens when hydrogen atoms, the white ones, and oxygen atoms actually get together on these tiny little dust grains. They move around, they find each other, they meet and greet. There? No. And then they form hydrogen peroxide and then water. And now we fast forward from a few days to, say, 10,000 years, 100,000 years, and that is how we make water actually on the surfaces of these grains. So we think actually that most of the water that is actually now present on Earth actually was formed in this way, already from the clouds before the formation of the solar system. As one of my colleagues called it, water is actually older than the sun itself. So think about it. The next time that you actually take a sip of water, you're drinking water molecules that are 4.5 billion years old. But we're seeing not just water, we're seeing also more complex molecules now in the ices, thanks to Webb. And in fact, we had a big press release on this a few months ago. It was called Cheers, because we had found also alcohol in space. We found there, one of the news agencies said that the Webb telescope had found margaritas in space. So think about that. If you want to tap a beer, you can go to the Orion Nebula. There's probably enough alcohol there for some 10 to the 27 bottles of whiskey. The only thing is it's not quite 40%, it's only about less than 1% in terms of the density. So just to summarize, there's a lot of water, there's a lot of organic material. Those building blocks are really very widespread. Now, the last few minutes, I will take you then how this material actually is being able to get to a new planetary system. So here we see these rotating disks, these beautiful disks that Stefano showed. And now we see these tiny little grains actually colliding with each other and growing. There we see them colliding with each other, we see them growing and with these ices. And that is how we make bigger and bigger systems. And eventually we will make the planetesimals and planets out of them. And then they are full of these molecules. So if you think of it, there's a wonderful synergy between what we see in the outer disk with the ALMA telescope and what we see in the inner disk now with JWST. So I like to think that if we form out of the cloud, we form this disk and eventually a planet. And if the planet is a big cake, say a cherry cake, then what we are doing now with Webb and with ALMA is find the ingredients, the water, the sugar, the flour, everything that we now need in order to build, make a cake actually. That is what we are now measuring actually with JWST. So water is clearly a key ingredient then, and that's why Stefano's observation was so incredibly important. Because close to the young star it's warm, further away it's cold, and where the ice line is, that's clearly where the giant planets are preferentially formed actually. But these ice-coated grains also bring material to the inner disk. Can we now see that? And the answer is yes. Here we see the same system, PDS 70, with the two young planets in it, but now seen with MIRI. Now we zoom into that inner part. And this is actually nice work by an Italian postdoc, Giulia Perotti, who actually made this discovery and saw the water in the very inner part where terrestrial planets are forming at this very moment. We actually have a very diverse chemistry. Some of these disks are rich in water, others in hydrocarbons. And if you just look at this here, we see here methane, we see ethane, actually, we see lots of acetylene, we even see benzene, and we see all of these molecules actually waving at us and saying, yes, we are present here in this disk, we are available to build new planetary systems. So we are now actually at a very exciting time where we are now having information on the material, the composition of the material that is available to build these new planets in these disks. Webb is actually also observing exoplanets, mature exoplanets. It's finding water, CO2, SO2 actually in there. And it's even being able to study the weather on exoplanets. And Webb is also able to go back home to our own solar system, to study Jupiter, to study water in the rest of our solar system. So I want to end here, and I hope to have given you a little bit of a taste that astronomy, science is extremely exciting. A very exciting time with Webb, with ALMA. It provides inspiration. It provides perspective, a sense of vulnerability. We're only that tiny little dot there in the space. A little bit of modesty and also tolerance, because in the end, we are all world citizens under the same beautiful sky. And certainly in this turbulent world, that's a very important message to remember. I thank you very much. Thank you.
Grazie.
Thank you. I would like to ask you a couple of questions, very quick questions, because we have seen the extraordinary and very recent progress that is taking place right now on these topics. And in your point of view, what should we expect as future important steps? If you could imagine, for example, what one of the young people here in this room may be studying in high school now, when they become a researcher and study these things, what they will focus their attention on. What do you believe, Stefano? Well, in my view, to answer this question, we have to consider the development of the new tools that will be made available to the next generations. I have one slide I wanted to show you where you can see a tool managed by Europe together with Chile. It is a new telescope that is being built. It will be built by ESO, the European Study Observatory, where I also worked. And this is a new telescope that will work in the visible or infrared, and the disk will be 30-meter diameter. That's the mirror, the radius of 30 meters. The biggest now is 10 meters, and we get to 39 meters made of 780 small hexagonal mirrors, 1.4 meter radius. It's a very complex thing, technologically speaking, but in 2029, let's say, this tool will be able to have an eye that will provide very clear images, very sharp images of the central areas of these protoplanetary disks. So I think that in terms of planet formation, we will have new eyes like this, and maybe another one, LGNVLA in 2040, that will make us able to observe planet formation at a scale that is similar to what we can see on the Earth in terms of Earth formation. And maybe another thing rapidly is that another big development that we will have in this field is to characterize the atmosphere of the planets that are already formed and to find a causal link between the formation process and the final product that are these atmospheres. This field is exploding, really, and many future astronomers will work in revealing this type of causal connection.
Ewine, cosa c'è nella tua sfera di cristallo sul
Ewine, what do you have in your crystal ball in the future of this sector?
Well, indeed,
Remove yours or
yes. So astronomy is driven basically by new facilities. That's essential. And the ELT is one example of them. But you may think JWST Webb took 30 years. So what comes after Webb? It has to be already on the drawing table, because if we want to have something by 2045 for the young people that are now, in kindergarten, then we have to start working for that. And it's being planned, a new successor, actually, to the Webb telescope. Yeah.
Un'ultima battuta.
A very last point. It is clear that research like this touches things that are very dear to us. It's our planet. Let's think about our life, any kind of life form that is known, that inhabits a planet. So this leads me to a question immediately. For you, even personally, what is the motivation pushing you to continue to work in this field? Stefano. Well, this is a wonderful question that we received in advance, so I had the time to think about it. I think there are many ways I may answer. I believe that what pushes me really to continue with this job is a desire, an innate passion to discover something that, as of today, nobody could ever find. There is this great pleasure in finding something that is totally new. So an astrophysic or physics or an astronomist are like the explorers from centuries ago. It's really the idea of finding something that for the very first time is revealing itself to me, that I'm looking at it, that I'm getting to know it. And then there is another point that to me is always fundamental in this type of research and in my work. I always mention that. It is an element that is very difficult to understand. It is mysterious in the universe, and it is the I that I am knowing, that I'm learning it, that I'm finding out about it. To me, it is always fundamental to see or to discover and not to see sometimes, so trying to seek this link that there is between this immense reality, so complex, so beautiful, so durable, and myself. And recently, this has become a big engine in the work that I do. And if you like, the essential element, to quote part of the meeting's motto this year, is also to work with people and with friends, in some cases, that have this same driver, this same motivation, this same desire to discover this immense part of reality that is the universe and to feel this link with oneself.
Wow, Stefano, you're a hard act to follow. But yes, the passion with which we do our job is certainly an important part of it. And I think in this time when we so often look down, or we look at our iPhone, you know, I like to look up and just wonder, you know, what is out there? What is our place there in this gigantic universe? If we stop asking those questions as a society, as a humankind, then we have lost something. If we are no longer asking these biggest questions, you know, we are explorers as humans. We want to know what is out there. And to me, that is one of the big you know, drivers, basically, for doing this research. I'm not going as far as sort of trying to detect life elsewhere. That's for the next generation. That's still probably going to take another 50 years or so. We are the first generation, actually, of humans that have the technology to do this, to answer this question. Is there life elsewhere in the universe? But it will still take some time. But at least we have the technology now. But just making this journey, basically, of being able to zoom in, where seeing planets form, seeing the complexity of the chemistry coming together, that's already fascinating. And that's giving a lot of satisfaction and driver for all that we're doing.
Davvero dobbiamo.
Well, thank you so much, Ewine and Stefano. I'm not sure that we all understood everything of what we were told tonight, but a couple of things I think were pretty clear. One is how fine is nature in forming these important things that are the planets, and how much work of attention towards reality lies behind this attempt to understand this. And the other point that has been understood is that there are still big open questions in the details of understanding, but also these big questions that Ewine mentioned. Is there life elsewhere? Will we ever be able to see it, to become aware of it? Well, we do not have answers. And when we find the answers to these questions, we will have more questions to which there will be no answers. So I believe that this unknown land, this unknown landscape is something that is essential for us as human beings. The fact that something exists beyond our understanding, something that is still waiting to be reached by human sight. The existence of this bigger thing is really essential, I believe. And if there is something that our work science can guarantee, is that this unknown land will always be there, something that will go beyond what we understand. I think that this was very clear from what Ewine and Stefano told us. They also showed it to us, and so we want to thank them again for this.
Fermi. Devo dare un avviso.
I have to give a very important announcement, which is the following. Each of us can help the meeting. The meeting is also made of these events leading us to the frontiers of universe, but it is a big reality, and it cannot exist without your contribution. One way you can contribute is to make a donation to the meeting. And you can do this at the Dona Ora station with the red heart symbol we are very familiar with, or you can say it. Donations must be made at these dedicated stations where volunteers are wearing the red T-shirt Dona Ora. And there is another point that was decided the other day, as at this particular moment in history, we really wonder how it is possible to build a dialogue of peace, and also Ewine mentioned that before. Well, we cannot remain indifferent before what Cardinal Pizzaballa said in his opening remarks at the meeting. And for this reason, the meeting will give part of the donations that will be collected during this week to the emergency in the Holy Land. Thank you and good evening.
Yeah. Okay, Dad. Thank you. Thank you. Yes. Ah, the photo. Ah. Okay. Oh, we still have our headphones on.
La civiltà dell'amore, fratelli e sorelle, costruite senza stancarvi mai questa civiltà. Lavorate per questo, pregate per questo, soffrite per questo.
Si è voltato improvvisamente la gente che era lì e ha detto: la gente che cosa dice che io sia? Chi dice che io sia? E voi chi dite che io sia?
Vi imploro, con umiltà e con fiducia, permettete a Cristo di parlare all'uomo.
Don Gius aveva capito il problema che avevo. Se la tua vocazione è vero, il tuo lavoro verrà fuori anche dai sassi.
di comunicare la fede agli altri, ma veramente insieme a loro riscoprire che cos'è la fede, che cos'è la fede per me. Portare Cristo agli altri, comunicarlo agli altri è l'unico modo che abbiamo per conoscerlo veramente.
L'iter communionis aiuta a comunicare all'esterno la ricchezza di vita, di giudizi, di tentativi, di opere che nascono dalle persone e dalle comunità. L'iter communionis è proprio la vita del movimento. Scrivete all'iter communionis le vostre esperienze, ci fate bene. Si è voltato improvvisamente alla gente che era lì e ha detto: la gente che cosa dice che io sia? Chi dice che io sia? E voi chi dite che io sia?
Vi imploro, con umiltà e con fiducia, permettete a Cristo di parlare all'uomo.
Don Gius aveva capito il problema che avevo. Se la tua vocazione è vero, il tuo lavoro verrà fuori anche dai sassi.
Comunicare la fede agli altri, ma veramente insieme a loro riscoprire che cos'è la fede, che cos'è la fede per me. Portare Cristo agli altri, comunicarlo agli altri è l'unico modo che abbiamo per conoscerlo veramente.
L'iter communionis aiuta a comunicare all'esterno la ricchezza di vita, di giudizi, di tentativi, di opere che nascono dalle persone e dalle comunità. L'iter communionis è proprio la vita del movimento. Scrivete all'iter communionis le vostre esperienze, ci fate bene.